Lesson 8.3.1, a statistical test for the difference in two population proportions. Introduction. Texting behavior. None of us should text while we drive. Some research suggests that women text more while they drive than men do. Other research says that men text more than women while they drive. Suppose that we are interested in investigating the texting behavior of men and women drivers. After making some observations, we begin to think that men send more texts while they drive than women. To investigate the possibility that men send more texts while they drive than women, we randomly sample the populations of men and women who text while they drive. Our data includes 85 men and 97 women who text while they drive. We find that 31 of the men and 22 of the women text frequently. That means they regularly send 7 or more text messages per week while they drive. Now we will conduct a test of the difference in two population proportions using our texting behavior sample data. Try these. Step 1. Determine the hypothesis, or the hypotheses. We will begin by determining the null and alternative hypotheses. The null hypothesis is the claim that the population proportions are equal. The alternative hypothesis is the claim that the population proportion of men who text frequently while they drive is larger than the population proportion of women who text frequently while they drive. Okay, what we just saw, guys, this is always how we set up this kind of problem. If we're trying to compare two different populations and do a hypothesis test, then the null hypothesis will always be that they're equal, and the alternative will always be one of three things: either that one is larger than the other, the second one is larger than the first, or that they are just not equal. Okay, so we're going to move on here. We would like to test the claim that the population proportion of men who text frequently while they drive is larger than the population proportion of women who text frequently while they drive. The parameter in this test is the difference in population proportions. Write a sentence for null hypothesis in terms of difference in the population proportions. The difference in the proportion of men let me actually save space by writing it this way. Of men versus women who text frequently while driving is 0. Okay, we're saying that their difference is 0. And again, the only way that two things can have a difference of 0 is if they are equal to each other. Okay, this is always the null hypothesis, okay? So now let's go to the alternative hypothesis. This is going to depend on what the problem, actually the researchers in the problem think is true. And it says here we would like to test the claim that the population proportion of men is larger than the population proportion of women who text frequently while driving. So the way we would write it is like this. So the alternative is the difference in the proportion of men versus women who text frequently while driving is positive. Okay, now why are we saying that it's positive? Because if we're saying that more men text while driving than women, then what we're claiming for our alternative is that if you take the proportion for men and you subtract the proportion for women, you get a positive number. So that's what I wrote here. You could also say greater than 0, right? That's another way to write that. Okay? Greater than 0 and positive are the same thing. Okay. So let's go on. It says step 2, collect the data. Next, we can determine whether the sample statistics satisfy the normality criteria and calculate the sample proportions and the difference between the sample proportions. Verify that each sample contains at least 10 successes and 10 failures. In our texting example, a success is a person who texts frequently while driving. Enter the values in each of the blanks below. Okay, for the men, how many successes and failures are there? Let's look at our sample. It says that 31, so the data said 85 men were sampled, and 31 of them text frequently. Okay, so 31. And how many failures are there? Remember, there were, let me see that again, there were 85, right? So we do 85 minus 31, and that tells you how many failures there are, right? 85 minus 31 is equal to 54. So that means there are 54 failures. What about for the women? Let's look. In the sample, it says 22 of the women text frequently out of 97, right? So there's 22 successes, and 97 minus 22 is 75. So this means there are 75 failures. So next part. Are these values large enough to assume approximate normality of the underlying sample distributions? Why or why not? Well, the answer is yes, since all 4 values are at least 10. Again, greater than or equal to 10, right? This means that if any of them are 10 or more, if all of them are 10 or more, then we could say that normality holds. Okay, let's keep going here. Calculate the sample statistics. So first we're going to compute the sample proportion for the men. So remember, for the men in the sample, there were 31 out of 85. So if we use our calculator, 31 divided by 85 is equal to 0.365. And if we compute the sample proportion for women, that is 22 out of 97, which is 0.227. So it looks like men text more than women in our sample, right? But remember, the sample is one thing. But when we compute a p-value, we want to know, is this strong enough evidence to lead us to say that with near certainty, right, with a high level of probability, this is true for the whole population, right? Not just for the sample, but for the whole population. So now what we want to do is we want to compute the difference, right? We want to see what PM hat minus PW hat is. So if we subtract 0.365 minus 0.227, what do we get? We get 0.138. Okay. All right. Next, assess the evidence. The test statistic for the hypothesis test is the z-score of the observed difference, PM hat minus PW hat. The null hypothesis for a difference in two, oh, by the way, before we move on, remember, M and W mean men and women, okay? So that's what those two things are talking about. So PM hat is just the proportion of men, PW hat is the proportion for women, okay? The null hypothesis for a difference in two proportions test generally claims that the proportions are equal. Under this assumption, the hypothetical common proportion is estimated by combining the samples to create a single proportion, P bar. This proportion is called the pooled estimate of the population proportion. So this pooled estimate, P bar, is given by this formula right here. You will not have to memorize any of these formulas. Remember, they will all be given on the exam. And remember, we're only going to use this when we're doing this, the standard error, okay? So that's what we're going to do. So the way that this looks, don't let this formula confuse you. This is just saying the number of successes for men plus the number of successes for women divided by the total number of men and women that were sampled. You add those together, okay? So what this is really doing is sort of treating the two samples like it's one large sample. Okay, so let's go back to our values and see what we got. 31 plus, there's 31 men that were successes and 22 women that were successes. So we have 31 plus 22 on top, and the bottom is 85 plus 97. So if we add those two together, let's be really careful, okay? You need to put parentheses here to distinguish that we are not adding two fractions together. This is a single fraction, okay? But we are adding the two numbers in top together, and we're adding the two numbers in the bottom together. You could do this all at once in your calculator, or you could just do this. Watch, 31 plus 22 is 53, so we have 53 successes. And then 85 plus 97 is 182. So what is 53 now divided by 182? We get 0.291. Okay, 0.291. So that's what we're going to use. And notice that 0.291 is actually in between the previous two numbers, right? Because we had 0.365 for the men and 0.227 for the women. This picks sort of a number in between them and uses that to approximate the standard error. Okay. We now need to estimate the standard error of differences as we have done before. Here, we will use the pooled proportion as the estimate for the proportion common to both populations. You can see below how this computation is performed. So guys, they did the math for us, but I want you to look at the formula. This square root formula is like the one that we used for the confidence intervals, right? The only difference is instead of using the two different P's, we're using P bar, okay? So when you plug in the numbers, that's what it looks like. And if you put that in your calculator, you will get this, 0.067. And again, this is the standard error of differences. It's the estimate for that. Okay, all of these are estimates because we do not know the real answer, remember. Okay, so under the assumption of equal population proportions, a collection of differences is simulated for our texting behavior example in the dot plot below. Why are we assuming that we have an equal population proportions? Because remember, we are assuming the null is true. Right? We always assume that the null hypothesis is true while doing a hypothesis test, and then we see what kind of a p-value we get, right? So if you assume the null is true, then that means what you would expect is this picture. In other words, you would expect to see that what occurs most often is the mean, where they're equal to each other. And then we expect differences that are bigger than 0 or smaller than 0 to occur more rarely, right? Each data point on the dot plot represents a difference in the proportions of men and women who text frequently while they drive. The proportion for the men are computed from samples of 85 randomly selected men who text while they drive, and the proportions for the women are computed from samples of size 97. And then remember, you do the men minus the women, and that's where you get the pictures in this dot, or sorry, the dots in this picture. Okay. All right, let's keep going here. Note that the assumption of equal population proportions yields a distribution of differences whose mean appears to be 0. Okay, so what did we observe in our samples? So that's what we're about to look at now. Place the difference computed in question 3C on the dot plot above. Is the difference observed in the sample data unusual? Explain. Well, what was the difference that we saw in question 3C? It's 0.138, right? 0.138. Where does 0.138 go? 0.138 is somewhere in here. Let me get a different color so you could see what I'm talking about here. Right, 0.138 is like 0.14, and that's between these two, so it's going to be right here. Okay, it's right there. So we placed it in the picture. So this question asks us, is the difference observed in the sample data unusual? Is it unusual? I mean, that looks unusual to me, right? That looks pretty far to the right, okay? Notice that there's not that many dots to the right of this. So yes, it does appear to be unusual. Yes. The observed difference appears to be unusual. Since it is far to the right. Oops. Since it is far to the right within the tail. Okay, so I said it appears to be unusual because we're not sure until we calculate the z-score, right? So that's what we're about to find out. Okay, how do you find a z-score? So the z-score of the difference, PM hat minus PW hat, provides an estimate of the number of standard errors the observed differences away from the assumed mean of differences, PM minus PW, which remember we're assuming is 0. As always, the z-score is computed by subtracting the mean and dividing by the estimated standard error. The resulting z-score is the test statistic for the two proportions test. So this is the formula for the z-score. Now, before you look at this and you think, oh no, this looks tricky, or I've never seen this before, I want to remind you that you've seen something just like this when you did hypothesis tests in module 7, right? So how did you do a z-score in that module? You took p hat and you subtracted p, and then you divided it by the standard deviation. Okay, and remember, you get this guy from the null. And you get this guy from the sample. Okay. Everything is the same now, except instead of a p hat or just a p, we have a difference. We have a pm hat minus pw hat, and we also have pm minus pw. Okay, so now this whole thing comes from the null, and this whole thing comes from the sample. Okay, so you see it really is the same thing. The only difference is you have two things that you're subtracting instead of just one thing. So what is this going to equal? Well, what was the proportion? What was PM hat minus PW hat? We actually haven't figured that out yet, right? But let's go ahead and figure that out now. What is PM hat? We did figure that out. PM hat is 0.365, and then PW hat is 0.227. Actually, we did already figure it out. Look at C. We subtracted them already. We got 0.138, right? So coming over here, 0.138, that's this. Now you're gonna like this part. What did the null say that those were equal to? Well, remember, we are assuming, guys, the null hypothesis is always assuming that they're equal. So if they're equal, that means that their difference is 0, isn't it, right? We're always assuming this. And so this is always going to be 0 when you're doing a hypothesis test and finding the z-score. So we're going to finish this down here because they want us to write it over here. So it's 0.138 minus 0, and then we're going to divide it by the standard error, which is 0.067, okay? And again, don't forget, 0.067 came from this formula, right? That big square root formula that they worked out for us. Okay. So we're going to divide this 0.138 minus 0 divided by 0.067. Something to note here is that when you subtract 0 from the top, it's going to end up not mattering anyway. But so the only thing you really need to put in your calculator is this. Okay, so just divide those two numbers. That's all you have to do. So when I divide the two numbers in my calculator, I get 2.06. 2.06. Okay. Does this z-score appear to be unusually high or low? Yes. Since 2.06 is greater than 2, I'll say greater than or equal to, it is unusually high. Remember, when something is more than 2 standard deviations away from the mean, we consider that unusually high. We can use a p-value to determine whether the z-score indicates that the observed difference in sample proportions deviates significantly from the assumed mean of differences. As we have seen previously, the p-value is the probability of observing a z-score that is at least as extreme as the test statistic under the assumption of a null hypothesis. If a p-value is small, less than or equal to alpha, we reject the null hypothesis and call the results statistically significant. For a right-tailed test, the p-value is the probability of observing a z-score that is greater than the test statistic. Find the p-value for the z-score you found in question 6. So remember, guys, I'm going to do a rough picture here so you can see what we're talking about. We are way over here at 2.06, and so what we're trying to find is that shaded area right there. Remember, we can do this using our favorite calculator function, normal CDF. So the p-value is equal to normal CDF. The lower limit is 2.06, and the upper limit is 1E99. Okay? So if we put this in our calculator, so I wanted to demonstrate this on the calculator. So again, normal CDF, we go second, DISTR, go down to normal CDF. My lower limit is 2.06. My upper limit is 1 second. The EE button, remember, is above the comma here, so it looks like an E99. We go down to paste and hit enter. I get 0.0196, which actually rounds to 0.020. Okay, 0.020. So we end up with 0.020, which remember is the same as 0.02. Some people might want to look at it that way. It makes it easier to look at what we are comparing it to. Okay. Before we move on, the code word for this lesson is driving. Okay, driving. As in driving a car. Number 9. Interpret the p-value in the context of this problem. So what does the p-value mean? Remember, the p-value means that we actually have 2% chance of observing something as extreme as what we did if we assume the null hypothesis is true. So in the context of the problem, it goes like this. If we assume, what was the null? Remember, the null hypothesis was that men and women text at the same rate. So if we assume that men and women text just as frequently while driving, the probability of observing the sample, or let me just say it this way, a sample or samples, sample differences. Here we go. Sample differences at least as extreme as the one we observed is 0.02. Right, now this is what we're saying. We're saying the chances of finding something as extreme as what we did or more extreme is 0.02, which is very unlikely. And so that's the whole point. We cannot, if we are assuming the null and that's what we get, it means the null must not be true. Okay. So let's go on here. Step 4, state a conclusion. Suppose we decide to conduct this hypothesis test at the 5% level of significance. Does the p-value indicate that the observed difference is statistically significant? Well, compare it. Isn't 0.02 less than 0.05? right? We're talking about a 5% level of significance, and our p-value was smaller. So this means, yes, the observed difference is statistically significant. Okay. Let's move on here. Using the p-value above and the level of significance, what can we conclude about the null hypothesis? So again, since 0.02 is less than 0.05, in other words, this is the same as saying the p-value is less than alpha. It's actually less than or equal to. If we get equal, we still err on the side of this. Okay? We reject the null hypothesis. And remember, when you reject the null, it means that you accept or you support the alternative. So we support the alternative hypothesis. Okay. So interpret the conclusion from the previous question in the context of the problem. Okay. Remember, we always have to write a full English sentence here that explains everything. So, at a 5% significance level, the evidence supports the claim So what did we show? What does the evidence support the claim? Remember, we're supporting the alternative. The alternative is that a higher proportion of men text while driving than women, right? That's what it means for the proportion of men minus the proportion of women to be positive, right? That the proportion of men, was it men in the US? Let me look at the original problem because I forgot. It's good to be specific here, right? You know what? It does not say what country these men and women are from that we're talking about. So let's just not mention the country since the problem doesn't either. So at a 5% significance level, the evidence supports the claim that the proportion of men who text frequently while driving is higher than for women. Okay. Again, when you reject a null and you support the alternative, this is how you write a full sentence, okay? If the p-value had been higher instead, we would have failed to reject the null and we would not support the alternative. So what we would write here is that the evidence, we fail to reject the claim that men and women drive at the same rate, right? Or we could say that we do not support the claim that men text more than women, right? We're not saying they text the same. We just are saying that the evidence isn't strong enough to conclude that men text more than women, right? Again, we're never proved the null is true. We either reject or fail to reject it, right? We would say not guilty. We wouldn't say innocent, okay? All right, everybody, I hope that is clear. Thank you so much for watching this video, and I hope it was helpful.